Okay, have you ever stopped to think about how a gigantic, high-quality video can just stream to your phone without instantly demolishing your data plan? Well, it's all thanks to this incredible hidden process, a kind of digital factory that takes that massive file and shrinks it down to a tiny fraction of its original size. So let's pull back the curtain and see how this shrinking machine actually works. No, really, think about it for a second. A single minute of raw, uncompressed 4K video could easily be tens of gigabytes. So how on earth can you have hours of video saved on your phone or stream a whole movie without your internet connection just giving up? The answer is this absolutely brilliant system of guessing, sorting, and, yeah, crushing information. For this explainer, I want you to imagine that the video encoder, the thing inside your phone or on Netflix's servers, is a giant factory. And it has one job, and one job only: to take an enormous, bulky video files, run them down a 4-station assembly line, and spit out a tiny, super efficient package of data on the other side. So here's our tour map. We're going to visit the 4 key stations on this assembly line, and then we're going to zoom out to see why this exact process is the engine that powers pretty much all the video you watch every single day. All right, let's step inside. The first thing to know is that video gets broken up into these little blocks of pixels, kind of like tiles. And each one of these blocks is about to start its journey down our digital assembly line. The whole thing kicks off at the prediction workshop. Here, the encoder makes a really, really clever guess about what the block is supposed to look like. But what comes out isn't the block itself, it's the error from that guess. It's this kind of ghostly afterimage called the residual. And this residual is the real raw material that's going to travel through the next 3 stations. Okay, so that ghostly residual arrives at station 2, the sorting machine. Now, this is important. This station's job is not to shrink the data. Not yet. Its only job is to sort it all out by importance. The best way to think about this is like a smoothie in a centrifuge. The raw residual is the mixed smoothie. All the important flavors and the plain water are jumbled together. This machine, the transform, spins it like crazy, separating that thick, flavorful pulp, that's our essential big picture info, from all the plain water, which represents the fine, noisy, less important details. The fancy, technical name for this centrifuge is the discrete cosine transform, or DCT. It just reorganizes the pixel data into a new grid of what are called frequency coefficients. But here's the key. So far, we have not lost a single drop of information. The smoothie can be perfectly remixed, everything has just been neatly sorted, no data has been harmed. Yet. So how does it sort? Well, you can imagine it's trying to paint the block using a set of special, wavy paintbrushes. The DCT's job is to figure out how much paint it needs from each brush. Brush 0 is just a flat color for the average brightness. Others add gentle waves for smooth gradients, all the way up to hyperwiggles for the sharpest, tiniest details. Now here it is. This is the crucial insight that makes this whole thing work. Most of the images and videos we see have big, smooth areas, right? Skies, walls, faces. That means to repaint them, you need a ton of that low-frequency flat paint. But you need very, very little of that high-frequency wiggly paint. So just like that, the most important information, our pulp, is now neatly separated from the less important detail, the water. And that brings us to station 3, the quality crusher. This is, without a doubt, the most brutal and most important stop on the assembly line. This is where we are going to trade quality for a smaller file size. See, up until this very moment, everything we've done has been perfectly reversible. But not here. At this station, we are going to permanently, irreversibly throw information away to get that massive file size reduction. There is no undo button for this step. The process itself is surprisingly simple, almost crude. The machine takes every single number from our sorted block and divides it by one single value. That value is called the quantization parameter, or QP. Just think of the QP as the aggressiveness dial for the crusher. The higher the QP, the more brutal the crush. And after dividing, it just rounds the answer to the nearest whole number. That's it. Let's just watch it happen with a really aggressive QT of 50. Our important pulp value, 158, gets divided by 50, which gives us 3.16. That rounds to 3. Okay, we've lost some precision, but the essence is still there. But now look at the water, the fine detail. A value of 12 divided by 50 is 0.24. That rounds to 0. A value of -2 also becomes 0. They are just gone, wiped out. So what's the result? The quality crusher has absolutely annihilated almost all of that fine, wiggly, unimportant detail, turning those values into a whole bunch of zeros. The block of data that comes out of this station is now incredibly sparse. It's mostly empty. So on to our final station, the zipper. After that, we'll flip things around and see how your device takes this tiny little package and tries to rebuild the original image. The zipper's job is really just cleanup. It needs to package this sparse block as efficiently as it can, and since the block is now mostly zeros, it uses a dead simple trick called run-length encoding. Instead of writing out 00000 63 times, which is obviously super inefficient, it just writes a tiny code like Z63. What was a long, clunky string of numbers becomes this tiny little two-part instruction. And that's pretty much it. That tiny, zipped-up package is what gets sent over the internet to your phone or your computer. Now, the decoder on your device gets this package, and its job is to reverse the whole assembly line. But can it really bring back what was crushed? Well, here's where we see the cold, hard math. The decoder tries to reinflate the numbers by doing the opposite of what the crusher did. It multiplies them by that same QP of 50. But when it gets to one of those zeros, well, 0 times 50 is still 0. That original detail, that value of 12 we started with, it can never, ever be recovered. And that right there is the fundamental truth of what we call lossy compression. The fine detail is gone forever. But by being so clever about sorting the data first, the shrinking machine makes sure that the stuff it throws away is the stuff our eyes are least likely to miss in the first place. It's a brilliant trade-off. So, we've finished our tour of the factory. Why does any of this matter? Well, because this four-step process isn't just one way to do things, it is the universal engine of literally all modern video. This exact pipeline, predict, transform, quantize, and entropy code, this is the fundamental recipe for every video standard you've ever used. From old DVDs to 4K Blu-rays to Netflix streaming and Zoom calls, they all just find smarter and smarter ways to make each station on this exact same assembly line more efficient. And this isn't some abstract computer science theory. This shrinking machine, this factory, is running in real time, billions and billions of times a second, all across the globe. It is what makes our connected, visual world even possible. Every single time you watch a video online, you are witnessing the output of this brilliant process of guessing, sorting, crushing, and packing. And that leaves us with a really fascinating question to chew on, doesn't it? The entire foundation of modern video is built on the idea of intelligently throwing information away. So as we keep pushing for higher resolutions and even better quality, the real challenge is, how do you get better and better at throwing things away?